Okay. People are going to keep stumbling in, and I'm going to have to keep adding them from the waiting room. All right, one thing you'll find handy moving forward. I mean, it's not the end of the world. I'm used to doing it in my other classes anyways, but if you join Zoom with your cuw.edu email, you won't get put in the waiting room. It'll just let you into the class, so I won't have to keep admitting people from the waiting room. But in any case, I'll just, I guess I'll announce it one more time. If your camera isn't on, turn it on for at least like the first 10 or 15 minutes of class so that the attendance checker thing can do its thing. Then I don't care what you do after that, but just make sure you get marked here is the punchline.
Yeah, okay.
Okay. So let's just kind of dive in. I'm Mike Littman. I'm your teacher for this thingy, and we have folks with all sorts of different backgrounds in this this class. So I give you some introductory stuff. So in the slide set, which is up on Blackboard, although I think my other class, one of my other classes, was having problems seeing slides from I'm not talking about the 549 problem. My 250 class this morning couldn't see the collaboration slides, but it looks like this set is connected. So I don't know if Apple's on the fritz this morning or something, but in any case, I have a link to the slides up on Blackboard. It's on the left-hand side of the main page. You should be able to click that and see my slides. I usually start off with kind of base set of slides, and then I start adding stuff randomly all over the place that ticks some people off. But I do it anyways. It's just kind of what happens. But at least you have a baseline of kind of the stuff I plan on talking about. So if you want to flip through there, you can, but no promises on what zigs and zags I might take as we go. But for, I mentioned we have folks with all sorts of different backgrounds. Especially a lot of our international students come from different undergrad majors, and it's not just international students. It's common among folks in master's programs where your undergrad's in one thing and then you decide to go get a master's in something else. Now, historically, the way it would work is people would apply for master's programs, and if your undergrad was in English or something like that, which obviously would be a very big disconnect, but you would be like conditionally admitted into a program, and then they'd say, okay, well, you have to take these 5 undergrad classes in order to catch up or whatever. Well, the problem is that our competition is not doing that. And hasn't for years. So we really can't do that. So we basically throw you into the deep end and just say, figure it out. So with that in mind, I try to cover some background information when I'm going through stuff, but I kind of focus on the idea that computer programming is like a baseline for almost all computer science. And it's important not to confuse that by saying programming, that computer science is programming, because it's not. I view computer programming as kind of like the tool that the computer scientist uses to solve our problems or to explore our field. But what I have here is, if you look at, I don't know, slide 2, is I have a link to the entire course, the entire class for our first, second, and third semester undergraduate programming classes, along with the slides. So I'd encourage you, if you have little to no background in computer science, you might want to go through those slides, and maybe you can hop around and practice the assignments and things like that. And I'm happy to look at the assignments or answer questions if you have them. But that very first class, CSC548, assumes you've never programmed before. So at the very least, that would be a good place for you to kind of play catch up. So one thing I do expect is that as master's students, you should be capable of teaching yourself. So even if you're coming in with a weaker background, play catch up yourself and get to where you need to be. But in any case, those resources are there for you. The other thing we use in the computer science department is we use Slack. So if you go to cuwcs.slack.com, it'll ask you to create an account. Use your Concordia email. That way it automatically lets you into the Slack channel. So create an account with that and then join the CSC548 channel. Once you download Slack, you can view it through a web page. You can download the app for Mac, for PC, for Android, for iOS. Once you're into the Slack channel here, if you go down by channels and hit the little dot things here, you can say browse channels and you can find 548. Just do a search for 548 in there and it'll show you that, and click it and that'll add you to that channel. You'll automatically be put in the general channel. All right, and I use 548 quite often. Let's see, what's this chat? I use 548 pretty often for making announcements for class and things like that, as opposed to email, because I can do it through Slack really quickly, where sending something through Blackboard is a little bit rougher on a mobile device and things like that. So make sure you have notifications turned on for Slack, because it will be helpful, as you might miss stuff that I put on there. Okay. So everybody, maybe, at some point today, jump on Slack and maybe introduce yourself in the channel, where you're from, all that stuff, just so we all kind of can meet each other. And that'll also prove that you now have access to Slack. Okay, then my overall academic dishonesty policy, kind of two sides to this. I encourage you to work together on homework assignments and things like that. I think learning is a group experience. You're going to hear stuff from me and maybe it makes sense. Maybe I go too quickly. Maybe you don't like the way I teach it. So sometimes working together can, add to the learning experience. So I do encourage you to do that for assignments and things like that. But when it comes to the exam, it should be your own work. Don't work in teams. Don't use the internet or cheat in other ways. I give the rules for the exam, because the exam is really my ability to kind of measure what you've learned in the class. So presuming you've done the homework, at least on your own or participated in your groups and things like that, you should have learned what you needed to learn to do reasonably on the exams. So do me a favor and abide by those rules. I'm pretty flexible when it comes to homework assignments and things like that, because I figure I'll catch you on the exam if you're not learning what you need to learn. So that's kind of the punchline there. So grade breakdown in the class, it's the grad classes are kind of problematic from a amount of time perspective. They're only 8-week classes, which means having a midterm and a final is kind of problematic. So basically 60% of your grade will be homework, then the final exam will be 40% of your grade, and the homework will prepare you for the final, is the idea. I'm not going to ask you stuff that's unrelated to what we covered in class. Okay. So I kind of like to start almost all of my classes off with this starting premise. And this is actually something, this is something I kind of created, but most of you are just starting, but another one of your professors will be Dr. Gary Locklear. And him and I have been in the department for a couple of minutes. I got here in 2006, and I think he's been here since 1840. Something like something like that. But in any case, one of his and him and I basically disagree on almost everything. And but the idea here is that he has this concept of the grand ideas of computer science, which I actually agree with. And so the way I kind of explain it is that we see so many repeating patterns in computer science that we just look at through different lenses depending on which course we're in or something like that. So in artificial intelligence, we're going to see the same things as we see in computer organization, the same things we'll see in database, so on and so forth, because the core components of computer science are there throughout, and just the way we experience them in these different classes, it might be through a different lens. So I like to kind of start off all my classes with this reminder idea of how do human beings solve problems, because we ultimately want to think about what's the job of a computer. You know, we don't just have computers for no good reason. I mean, sure, we've kind of turned them into forms of entertainment and things like that. But what was the starting point? The starting point was that a computer makes our lives easier. It solves problems more quickly or more tedious problems. It solves them more quickly, more accurately, yada, yada, yada. So at the end of the day, a computer is really a tool that a human being uses to solve problems. Whatever problems are kind of appropriate for a computer. So I like to start off with this concept of how do human beings solve problems, because whether we're talking about the computer itself or a programming language or the various tools, that software applications that already exist on computers, they're trying to mimic the way human beings already do stuff, but just kind of be better at what we suck at. Something like that. You know, I don't believe that it's going to ever replace us, because I think human intelligence is pretty unique. But at the same time, there are things that we suck at, and a computer can do those tedious things with less errors better than us. So as a human being, when we're solving problems, we use our memory. So we use our brain. We remember different pieces of information. We all know our name, things like that. People ask us quick pieces of information. We have it stuck in there, and some things are more important than others. So, those things are kind of in the forefront. We ask a lot of questions, and we repeat tasks. So a lot of the stuff we do on our daily lives, it almost becomes mundane for us, is a lot of repetition, even just like something like walking. You know, when you're walking, you're just repeating the same movements over and over and over again. So if we just kind of break down the way human beings solve problems on a daily basis, it falls into like one of these three categories, let's say roughly. I'm sure you can sit there and expand this out or get more granular or something, but at the high level, I think this makes some reasonable sense. So when we think about the job of a programming language, and we really could replace this with the job of a computer in general, but I write it in terms of programming languages here. So this is allow us to tell a computer what to do. And this course is going to be a lot about the language that a computer speaks relative to the language that a human being speaks. And languages come in different formats. They're not all programming languages. So for instance, those of you from Hyderabad in here, your core language that you speak most of the time is going to be Telugu, right? So all of you speak Telugu. Now, you know, your national language is Hindi. Now, just to your east, you have Tamil, right? So, but for those, a lot of you don't speak Tamil. You speak Telugu, and if somebody speaks Tamil, you guys can't talk to each other. So historically, you would have you would have used some other common language like Hindi. Now you just use English, right? When I was in Hyderabad, I was walking around like malls and stuff, and just everybody's speaking to each other in English. They don't even waste their time in Telugu anymore. It's just it's just the thing.
So you've been into India?
Of course. Who wouldn't go to?
That's great.
Wouldn't go to India.
It's a Hyderabad biryani. Yeah.
Well, actually, it's, I mean, I think I was there. I mean, you guys would have been, some of you would have been sophomores in college or juniors, maybe. I mean, did any of you have me come and speak at your school? I think we have a couple of new
So,
intakes that are students that I met when I was over there. But yeah, I
Shiva
was,
Krishna.
yeah, well, yeah, Shiva and I are good buddies.
Yeah.
I think some of you were texting pictures because him and I had had
Yeah.
lunch. We had lunch that day after I gave my presentation the other day.
Yeah. In last subject, it's like computer networks. You gave an introduction of that.
Yeah.
Your friends, your food. Yeah.
But in any case, yeah, I spent some time over in India. That's a very interesting interesting place to visit. I don't know that I'd want to live there, especially not during the summer. Yeah, because it's about 4,000 degrees.
We are glad that you liked it, Michael.
Well, I'm a big fan of food.
Oh,
There's a lot. Indian food is very good, so that's one thing you guys got right. Is
great.
is the food, but I still stand by that the
Mutton biryani.
yeah, for an American, you can only have biryani so much. I mean, you can't just have this one dish that you just say we're going to force feed this to you forever. I was eating biryani for breakfast. It was terrible. All right. So in any case, when we think about the job of a programming language, ultimately we're telling a computer what to do. Just like right now, we're choosing English because that's the only language I speak. If we were over in Hyderabad, actually, all your schools in English now too, but you get the point. You know, if we happen to both speak a different language like Telugu, maybe we'd be communicating in Telugu. Okay, but we had to pick a common denominator that everybody in this room, you know, at least roughly understands. I know the folks from India, you've had English for years and years and years. So your conversational English is strong, but maybe your written English and things like that is not as strong. You know, but it's still way better than my written Telugu. So we're gonna stick with a language that we both understand because we need to be able to communicate with each other. You know, or in this case, I need to be able to tell you what to do in terms of here, do this homework assignment, yada, yada, yada. All right. So the same thing's true when we're dealing with computers. We need to have some way of telling a computer what to do. And we have various tools for doing this, but the issue is, and this is where I think folks get intimidated by computers until you get deep enough into computer science that you realize that computer languages are actually simpler than human languages, natural languages. All right, so, and I feel like I'm almost the, maybe the poster boy for this in a weird way. I have a lot of interest in learning other natural languages. And I always joke saying, oh, I'm fluent in Telugu or fluent in Urdu and stuff, where I only know the bad words. And the reality is that I am envious of people who can learn other natural languages, especially the ones that can do it quickly. I'm terrible at it. I mean, I got decent grades in, like, you know, high school Spanish and stuff, but I mean, I don't know it. I barely know enough to order at Taco Bell. You know, and but the idea is, it's just I feel like especially terrible at learning natural languages, but I feel like I'm especially good at learning programming languages. They come significantly easier to me, and they almost come trivially to me, programming languages. So that's almost evidence, you know, if we just assume that I'm this like simple-minded creature, you know, that's almost evidence that computer languages are so much easier than natural languages, because they're solving a much smaller subset of problems, and we're different animals. We're human beings, the computer is a computer. We're not starting off on an equal playing field, where when we're picking a natural language and we're trying to decide how we communicate, human beings are complex critters, and you know, we need pretty rich languages in order to fully express ourselves. And then on top of that, we have things like facial expressions and hand gestures, and I'm just sitting here waving my hands around and stuff. You know, we have all sorts of more complicated levels of communication that human beings use. So really, human language is orders of magnitude more complex than the ways that we communicate to a computer. Now, having said that, at some level, we need to understand, how does a computer actually communicate? Now, at the once we get past all the software and everything like that, so we get down to the bare bones, we're dealing with zeros and ones, and that's something we're going to talk about in here once we get into the nitty gritty. So we're dealing with zeros and ones, and that's not our cup of tea as human beings. If we just were sitting there tapping out zeros and ones, we have the 2-button keyboard, that's not going to be good for us. We're going to make a lot of mistakes. That's not our kind of processing. We paint the world in kind of broad strokes as human beings. So we're going to need tools that sit between us and those zeros and ones. And, you know, depending on the lens we're looking at, what class we're sitting in, how far removed from those zeros and ones and what tools we're using is going to kind of tell us the field that we're looking at. So what this class is really thinking about is, now many of you had an undergraduate class that really talked about the super details. I'll be recovering some of those things, but specifically in this class, we want to think about some of the decisions that needed to be made specifically with mobile computing. You know, with these computers that were, I'm waving my phone around, these computers that we're carrying around in our pocket, and, you know, what trade-offs we've had to make and how that's evolved and that kind of stuff. Okay, but the point still remains that when we think about our smartphone, we are interfacing with that through this, you know, touch screen and all this software and stuff like that. But at the end of the day, it dives down into zeros and ones. Okay. All right. So whatever kind of language, or you want to replace language with software tool or operating system or whatever tool we're using on a computer is an intermediary for us to ultimately tell a computer what to do. And it's as human beings, we've built up layers that hopefully allows us to more conveniently communicate with the computer so that we don't have to speak zeros and ones, because that's not our cup of tea. All right, that makes sense. So the second statement is kind of the kicker. So a programming language is a power tool that converts our problem solving skills into something a computer understands. And we don't care that a computer is at a disadvantage in this you know, this collaboration. All right, so, you know, we're okay putting all these like levels of software and filters and things like that, so ultimately whatever we say gets down to those zeros and ones. We don't care that computers are, you know, have trouble dealing with natural languages. They can just, you know, be disadvantaged. It's fine. So when we think about our modern day programming languages, and similarly, I talk about it from a programming language perspective because it gives us a foundation that is across computer science. Like I mentioned, that, you know, programming is the tool that computer scientists use to solve problems. It's not computer science itself. But to talk about this mapping, since human beings solve problems using memory, asking questions, and repetition, that means 100% of programming languages will have facilities for these three things to try to mimic the way human beings solve problems, right? It's going to give us something usually called variables for memory. So the ability to describe name value pairs so that we can tell the computer to hold on to some information, and where they're going to put that information is something we talk about in here. So is this going into a hardware register? Is this going into an L1 cache, an L2 cache, an L3 cache, system memory? Is it going onto the hard drive? You know, the farther removed you get from the CPU, the slower and bigger the memory tends to get. So where is the right place to put different things that we need to remember so that A, it's readily available for your problem solving, and B, it's fast enough to accomplish what you're trying to accomplish? So we'll talk about some of that. But at the end of the day, we're still talking about the computer remembering pieces of information somehow. Similarly, we ask a lot of questions. So computer languages represent this through something called conditionals. And if we're thinking about one of our high-level modern languages like Java or C#, we have if statements. But if you go all the way down to the assembly language level, where we're dealing with, you know, just kind of one layer removed from the zeros and ones, we still have ways of effectively asking questions. So this has been something that we've been doing in our communication with computers for a long time. We've just continued to evolve those structures to make it more and more convenient for us. We don't even think about the computer's feelings. All right. Similarly, repetition, so in our modern stuff, we have loops, functions, subroutines, procedures, methods, whatever you want to call them. And it doesn't matter, like I said, if you're using modern languages like Java or C# or Python, pick your poison. They're all going to have facilities for looping stuff and functions and this kind of thing. You go all the way down to the assembly language, that one layer removed from the zeros and ones. You're going to have the same constructs. There may be a little bit less convenient to work with. At some point, we'll look at some assembly language. Probably earlier on, and then we'll do some assembly language a little bit later on. And specifically, we're going to be looking at ARM assembly language, which is something that all our mobile chips use today. We'll talk about all that. But in any case, even though we get to just one layer removed from the zeros and ones, we still see that it's very humanized, even though we might not like it, because assembly language feels difficult, cryptic, not fun to program in that or something like that, but it's still way better than zeros and ones. All right, so kind of what we talk about in here at various levels is going to be ultimately how are those zeros and ones represented, so that we understand what those assembly language things are actually trying to accomplish. Okay, but as our starting point here, we do want to think about that no matter what tool we're using on our computer, whether it's a programming language, which is kind of an open-ended thing for us to tell a computer anything we want, or we're using a specific software package like MySQL for databases, or Microsoft Word, or right here I'm using Keynote or PowerPoint, whatever it is, all of these different software packages are just abstractions that ultimately get us down to telling a computer what to do. All right. So under the hood, no matter what we're doing on a computer, we eventually bump into zeros and ones, and those zeros and ones are stored in some kind of memory. And we have some sort of representation of a language that ultimately tells that computer what to do in terms of the things it knows how to do. At some point, we'll talk about, well, I'll mention it now. We'll probably bump into it. So this is where I kind of magically throw extra slides in, just because my mind has gone to this level right now. So we talk about the CPU. So what is the CPU? Tell me about this guy. So based on what you've historically learned, tell me about the CPU.
It's like a control processing unit.
Okay, so yeah, we always start off with what does it stand for, right? Control processing unit. Okay. Yeah, we can just stop there and say we're good. What does the CPU do? What's the job of the CPU?
All the operations are held by CPU.
Okay, I kind of like that. All the operations are held by the CPU. All right, and I'm going to expand on that actually here in a minute, because that really is pretty close. A lot of the things people will say, they'll use like broad strokes and say something like, it's the brain of the computer.
It executes instructions.
They'll say something like it's the brain of the computer, or
Yeah, it's
like that.
CPU performs calculations and runs
In
programs.
this way, we can say a thinking process of the
The
computer.
instructions.
All right, calculations,
And
Okay.
runs programs.
runs programs. Okay. Yeah, so now we're starting to get into some of the gray area there. When does the CPU stop and where does the operating system begin, and some layers there in between. So I like to think of the CPU as a collection of magic tricks. So those of you who've had me in undergrad classes have heard me say this plenty of times. And this is actually very related to the statement here. All the operations are held by the CPU. So I'm calling these operations, I'm calling them magic tricks. So I'm saying where a magic trick solves a very tiny problem that is not overly useful in and of itself, but when combined with a bunch of other magic tricks, can solve complex problems. So if we think about the job that the folks who make these processors has to solve, so whether you're Intel or Intel's still a big player. Apple has we're going to talk some about Apple's newest processors, the M1 processors, which are I'm a big fan. They're going to revolutionize the way that we think about processors moving forward. We're already seeing Intel and Qualcomm kind of try to duplicate what Apple has done with the M1 processor. So this is less about a pro Apple statement and more about the next generation of our computer architecture. And really, if you and I don't want to give too much away here because we are going to talk fairly in depth about the M1 processors. But if you look at Apple's processors that their computers are coming with today, these M1 chips, they're almost the poster boy for this class, because they are showing some of the decisions that need to be made at the computation level, at the CPU level, at the architecture level, for mobile computing. Because anymore, when we think about a computer, if somebody says, "Oh, my computer is having a problem," our mindset typically goes to it's probably a laptop. Or historically, we would have said a computer was a desktop. And some people might have a laptop. Now, most people's computers are laptops. The folks who have desktop computers, in general, are people who are maybe gamers. So they build a desktop computer or something like that because they can put the strongest graphics cards and all sorts of stuff like that in it. So really, a desktop computer, in many ways, has started to become more of a special purpose machine for video game players, whereas laptops are kind of our workhorse computers that we're using a majority of the time. The other people who have desktops are maybe people who are working with really computationally intensive type things, because at the end of the day, you can fit more power into a desktop than you can into a laptop. But you know what, it's that line is getting pretty blurred. So depending on what your background is here in computer science, this might be overly meaningful to you, or this might be lost in you. But so I'm on a laptop here, and I happen to be on a Mac, but I'm not necessarily pro Mac. I'm pro convenience. So this is one computer that I can carry around. That effectively can be 5 or 6 different computers running virtual machines, Windows, Linux, all sorts of things. And I only have to schlep around one computer. Okay, so I'm on a 16-inch MacBook Pro. So I have an 8-core i9 processor from Intel. So highest end Intel processor. That's 16 logical cores. I have 64 gigs of RAM. Effectively, this is a really powerful computer, and it's a laptop. All right. And this computer here is actually a good example of, this is less about mobile and more about just computing architecture, is we want to think about these things as just resources. This guy right here, our CPU, this processor, this is a computational resource. And this particular resource can logically do 16 things at once with a 16 logical core, 8 physical core processor. And each of those cores can operate at 2.4 gigahertz, but it's based on this i9 architecture. And we'll talk about what some of those words mean as we go in here. But this dude here represents the computational power of our processor. So this is this thing that is all the operations that we have. So the CPU, or in this case, my 8 CPUs I have in this computer, they all have this collection of magic tricks. The same collection, we just have 8 different workers. So it's kind of like if you're on if you are shoveling snow, since I know many of you, maybe you saw your first snow since you've been here on in the United States. You don't get a lot of snow in Hyderabad, right? So
Right, sir.
I had a student was it last semester? Or, no, must have been last spring. And I think also from Hyderabad, but definitely somewhere from India, but I'm pretty sure Hyderabad. And we had a bad ice storm. And oh, he freaked out. We had a class, and I had to like drive him home and stuff. He was upset. Basically thought the world was ending. It was the perception he had based on what was happening outside. All right. So in any case, this guy here is my collection of little tiny magic tricks that my computer is capable of performing, none of which are overly interesting. Okay, they don't do that much. If you look at one of those magic tricks, like, oh, well, that's not that interesting. The way I usually describe it is, you put your hand up, how many of you can do that? You can wiggle your thumb. How many of you can do that? These little tiny things, like nobody's impressed if you're standing there wiggling your thumb like this, right? It's not an impressive maneuver. But when you think about it, how many of those little tiny, it's being blocked. I have my coffee mug here, I promise. How many of those little tiny maneuvers need to be put together in order for me to pick up my coffee mug? That's what I'm saying about those magic tricks. I have these little tiny abilities that my hand can do. And when I put those together in a certain order, in a certain way, I can accomplish a tangible task, like picking up a coffee mug, something like that. All right. So that's what this dude is really about, is that collection of magic tricks. How many of those workers I have. So I was talking about like shoveling snow. Okay, so if we're shoveling snow at the university, they bring a truck in and drag stuff around. But let's go old school and say that, what we did is we just got a whole bunch of students together and say shovel all the driveways or the parking spots, whatever. In my example here, I would get 8 students. I would recruit 8 different students, all who had the skill set of shoveling snow. Okay, and we'll say they all shovel snow at the same rate. So I get 8 effectively identically performing students who all know how to shovel snow. And I can have each one of those students work on a different part of campus shoveling. All right, so we are doing the same job 8 times over. All right, we have, we'll end up accomplishing some tasks like that more quickly. All right, as opposed to the old joke, how many people does it take to change a light bulb? So if we say that all these students, these human beings who have, all those, the ability to do things with their hand, wiggle their thumb, stuff like that. And we say, okay, all of them are capable of doing the various maneuvers necessary to change a light bulb. Are we going to really change a light bulb more quickly if all 8 students are working on that single task? No, it only takes one person to change a light bulb. So that would be an example of, just because we have a whole bunch of workers, we have the resources, the computing resources available to do something, doesn't mean we'll always be able to take full advantage of those resources, but they're still there for when we need them. All right, so this line right here deals with my computing resource, my CPU. This line right here, 64 gigs of RAM, this deals with my computer's ability to remember things. Okay. And that is kind of in conjunction with my storage. So I also have 1 terabyte of storage. So this is more long-term ability to remember things. And this is more short-term ability and faster ability to remember things. All right. And then there's some memory hidden on this guy too. That's super, super fast, but isn't even the size of which isn't really worth talking about a majority of the time. Because it's just used super temporarily while we're doing those little magic tricks. Okay, but at the end of the day, when we think about a computer, we're really thinking about a collection of resources that we can utilize in order to solve problems. Okay, and all those resources ultimately come down to remembering things, asking questions, and repetition, and having tools for doing those things. All right, so when we think about our CPUs, what we're really thinking about is a processor having this collection of operations or this collection of magic tricks that is dictated by whatever the architecture is. So if we are On your cell phone, you're probably running, if you're on an iPhone, you're running one of Apple's architecture, their A series chips, which is ARM compliant. If you're on a Qualcomm, Android phone, you're probably running one of the Qualcomm chips, which is also ARM compliant. So they're actually sharing a core architecture, but the makeup of the processors are different. They've made some design decisions, and we'll talk about some of those things. But they do share an architecture, whereas like this computer here is running an Intel processor, an i9, and so that's running the x86 architecture. So the Intel collection of magic tricks, which every single year when they come out with the next generation of processor, they might add or change some of the old magic tricks where they can say, okay, well, this year's processor is up to 140% faster than last year's. Well, it's not 140% faster across the board. There's probably one little magic trick that technically does something way faster than it did last year, and is only going to benefit people in this very specific kind of problem solving. But at the end of the day, they can say it's up to 140% faster, because that one little magic trick, which only helps people doing this one specific task that only one person on the planet might ever do, can take advantage of that in the latest generation processor. With that in mind, if you have built a gaming computer, for example, and you have last year's generation of the Core i7 processor from Intel, and this year's generation comes out, and somebody said, well, should I update to that? I'm almost 100% of the time, I'm going to say no. You're not going to get really any benefit from that for anything that the average person does, even the gaming user does on a daily basis. They're effectively the same chips. Maybe they'll use a little bit less electricity, or maybe they've gained a little bit of clock speed or something like that. But generally speaking, you're not going to see a performance difference. So why let your bank account get smaller? It would be kind of the argument. Okay. Whereas, so this is running an Intel-based architecture where I have a MacBook Air sitting across the room here that I drag with me to coffee shops, because this computer I have here, which is actually pretty portable. So I don't know, the MacBook Air is probably overkill, but I usually leave this computer at the office. But I've been home for a couple of days because I'm helping a friend who broke his leg do things around the, get to doctor's appointments and stuff. But I usually leave this computer at my office, and I have this other one for going to coffee shops or whatever. But in any case, my other computer is one of Apple's newer laptops, less powerful than this one, but it's running one of their M1 processors, which is an ARM-based architecture. So it's not architecturally compatible with this computer. They're effectively speaking different languages. Now, they both roughly are able to perform the same magic tricks, right? But the way they accomplish those magic tricks, well, actually, that's probably the wrong way of saying it. They both ultimately can solve the same general purpose problems, but the way they ultimately accomplish solving those problems involves maybe a different collection of magic tricks or a different order or something like that. But, in any case, it's, those are design decisions. And just to kind of give you a little bit of a foreshadowing of where we're going, if you notice here on my computer, so we've been in class for, 52 minutes now. And my computer right here, I'm on battery life since I'm huddled by the coffee maker. I'm at 54% battery life. Now I turn up my screen brightness all the way because I have I'm older eyes. So obviously I'm using the screen a little bit, the backlighting of my screen a little bit more, but I'll tell you what, I do the same thing on the other computer. If we were in the same Zoom meeting and I was on my MacBook Air, what do you think my battery life would be right now at 53 minutes in? Anybody have a guess? So this computer is at 54%. What do you think my battery life would be on my MacBook Air running an M1 processor?
It would be around 60%.
You think 60%?
Yeah.
More than 70.
49.
70, what, anybody else?
49.
While I
40.
read the poll, I think
90.
65. It would be 65.
It might still be at 100%, but it would probably be at 99%. It is ridiculous how power efficient the M1 processor is. Like almost impossibly so for doing tasks like this. Okay, because these are just business tasks that I'm doing, right? You know, I'm not playing a video game where I'm really stressing the CPU or stressing the graphics card or something like that. I mean, because if I was on that other computer and I was trying to play a video game, the battery would drain much more quickly. But for your average task that you're using your computer for, like this, I'm doing a slideshow over a Zoom meeting. You know, this is not mind-bending type work, right? That computer lasts forever. I probably get, I don't know, 30 hours battery life, 40 hours of battery life. It's ridiculous. So that's why I said earlier, you know, I'm a big fan of that processor and of Apple's new architecture moving forward for mobile computing, because most of our mobile computing is work like this: checking email, doing web browser. Even if you're a computer programmer, you're sitting there writing software, most of that is effectively the same thing as like writing a book, right? You're just typing stuff. You know, maybe if you're doing stuff with lots of graphics and you're hold on, let me check this real quick. My buddy who one second, sorry. This is definitely Blade style, Emily. His ride to his doctor's appointment dropped him off at the wrong hospital. So he's in the lobby of the wrong place and needs to get to a different place. I'm just finding out what time to see how much longer we should go today. Okay. All right, so I'm gonna finish up here because I gotta go get him over to his other place. So let me just finish up in the next like 2 minutes so I can go grab him. Sorry about that. It's one of our other faculty members broke his leg in an ice storm a couple weeks ago, and his other friend dropped him off at the wrong hospital. It's kind of I guess kind of funny, but actually not out of character. But in any case, I was saying that I'm a big advocate of this M1 processor from a mobile computing perspective because of how well it performs for a lot of our business tasks. And it really is shockingly so. But I'm also a big advocate of competition. So I don't want Apple to rule the roost when it comes to processors. I'm okay with them being innovative and kind of being first there. I don't even care if they're the winner. Right? But we want our other processor makers like Intel and Qualcomm, we want them to be learning from some of the cool things that Apple's done and then duplicating those things and maybe coming up with new innovations themselves. That's what we've seen. If for some of you are iPhone users, others are Android users, you know, we've seen that over the years. When iPhone first came out, for the first many years, it was a substantially better product than Android. Even though the Android people were saying, oh, our Android's better, yada, 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 all the commercials said that. It wasn't. Apple was a superior product. Well, now over the years, Android has stolen some stuff from Apple, made it equivalent. came up with his own innovations, which Apple then stole back, so on and so forth. Where today, whether you're an iPhone user or an Android user, you're using a very capable device that you could legitimately argue that, oh, I like this device because of X, Y, and Z, where I like this one because of A, B, and C. And those are legitimate arguments you could have. So those are some of the things we're going to talk about. Okay, so in any case, like I said, I got to go schlep this guy to his other appointment. I apologize for that. I wasn't supposed to pick him up until like 10:30. But in any case, we'll come back on Thursday, same time, same station. In the meantime, make sure you are getting onto our Slack channel and go ahead and introduce yourself. I have a link to, I'll be putting up the recording of this video, so you can go back and rewatch it. It helps you go to sleep at night, things like that. I already have a link to the YouTube playlist on the Blackboard thing. So make sure you can log into Blackboard and all that stuff. If you are having any problems with any of those things, post it in Slack, send me a private message, or you can email me and we'll get you fixed up. Let's try to get everybody with access to everything this first week so we don't have to do a lot of management moving forward. Sound good? All right, questions, comments, concerns, bribes? Okay.
Good.
Well,
Thank you so much, sir. The class was very interesting.
all right, well, I will see everybody on Thursday, and sorry to have to cut you a little bit short, but it is funny.
Hey, Professor Lemon,
Sure, go ahead.
good luck with playing.
Say this again?
Say good luck with playing.
Oh, he's fine, and I only live 3 minutes from the hospital where he got dropped off in the wrong place, so it is fine.
So wait, Blaine got hurt, or who was?
It's Blade.
Okay.
Yeah, Yiming Liao.
Yeah.
During the ice storm last week or 2 weeks ago, whenever it was, he slipped on the ice in his parking lot. Broke his leg. So yeah,
Yeah, I can see it's a problem. That's awful. It's bad luck.
Yeah, but he's already had surgery to fix it, and he's in a cast. This is
Right.
his follow-up appointments. He'll live.
Okay.
All right. I will
Good,
see
sir.
everybody on Thursday.
All right.
Take care.
Take care.
Take care.
Take
Take
care.
care. Bye bye.